Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 9th, 2026, just about 4 days ago. It proposes a fascinating new theory that effective long chain of thought reasoning resembles stable molecular structures, comprised of deep reasoning, self-reflection, and self-exploration bonds, rather than just simple linear sequences. The paper is titled, The Molecular Structure of Thought, Mapping the Topology of Long Chain of Thought Reasoning. And as we'll see later, the resulting method, called Mole-Syn, significantly boosts performance and stability across benchmarks. Figure 1 visualizes this molecular theory by mapping reasoning behaviors to specific chemical interactions. The first panel shows self-exploration as van der Waals forces, representing loose, tentative connections between concepts. In the center, deep reasoning appears as covalent bonding, creating a strong, linear, logical backbone. Then, the third panel illustrates self-reflection, where the chain folds back to link with previous nodes for error correction. The column on the far right provides text examples, showing how these abstract structures translate into actual language generation. Figure 2 contrasts this new perspective with traditional models. On the left, standard chain and tree structures treat reasoning as simple sequences of nodes. However, the large panel on the right illustrates the proposed molecular structure reasoning. Here, Molecule 0 connects to Molecule 1 through self-exploration, essentially probing new logical territories. Then self-reflection allows the chain to fold back and optimize itself into Molecule 0+, fixing errors much like chemical bonds stabilize a molecule. To verify if this structure is universal, Figure 5 compares the behavior patterns of 3 distinct models. On the left, we have the transition matrix for DeepSeek R1, followed by an OpenAI OSS model in the center and QWQ on the right. These grids map the probability of switching between states, such as moving from deep reasoning to self-reflection. Crucially, the color patterns are nearly identical across the board. This visual similarity corresponds to a statistical correlation of over 0.9, suggesting that all effective reasoning models converge on the same stable, underlying topology. Well, having established that reasoning topology converges, Table 1 now tests if these different structures actually yield the same results. It compares performance on 6 benchmarks when Llama 3.1 is fine-tuned on data distilled from R1, OSS, and QWQ. In the top section for the base model, using 20,000 samples of OSS data, yields an average score of nearly 34%. This is notably higher than the roughly 20% achieved by R1 or QWQ, which suggests that distinct semantic isomers matter significantly for learning efficiency. So, Figure 12 demonstrates the continual improvement of these models during reinforcement learning. Panel A on the left compares accuracy across different setups, where the pink and purple bars show that models initialized with Mole-Syn achieve nearly 40% accuracy after reinforcement learning, matching the standard distillation baselines shown in yellow. Then, the 3-line charts on the right track the training dynamics over 1,000 steps. We see a clear, steady rise in reward, response length, and accuracy, which confirms that the synthesized molecular structures provide a robust foundation for sustained learning. While Figure 12 focused on reinforcement learning dynamics, Table 2 provides a comprehensive performance comparison across 6 benchmarks, such as GSM 8K and Math 500. The table is divided into 2 main sections. The top block reports results for the base Llama 3.1 model, while the bottom block covers the instruct version. A crucial finding appears in the base model section when comparing standard distillation in green against the new Mole-Syn method in purple. Specifically, training with synthetic QWQ Mole-Syn data yields an average score of roughly 22%. This actually surpasses the 21% achieved by direct distillation from QWQ, demonstrating that structurally guided synthesis can be more effective than raw imitation. So, to conclude, the key insight here is that robust reasoning relies on a stable, folded topology rather than just linear token sequences. By explicitly modeling these molecular structures, the Mole-Syn framework offers a way to transfer complex reasoning skills without the instability of standard distillation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.